Hello guys, welcome to this video session of modeling road loads using Simscape Toolbox. So here in this model, we are going to calculate different road loads like rolling resistance force, aerodynamic drag force, hill climbing force. And then based on a closed loop system, we are going to simulate the system. So this is the model which we are going to model today. So let's start. So now we will create a new model. So to create a new model, we will use a command to open a Simscape blank model, that is ssc_new. Once I clicked it, you can see a blank Simscape window has been created. Let me just maximize this. So you can see it has been created and it has been opened. Now we'll start calculating or modeling different subsystems for different road load calculation. So first we will start with uh, gradient aerodynamic drag force. So the equation for aerodynamic drag force equals to FAD equals to half into rho into A into CD into V square. Okay. So let me tell you what thing is defined what. So let me just maximize the size a bit. So here V is nothing but the velocity of the vehicle. CD is the drag coefficient. It depends on the vehicle aerodynamic structure. It varies based on the vehicle structure. This A is nothing but the frontal area of the vehicle. Rho is the air density and half is a constant value. So we will start modeling this. First, we will take one connection port to give the input as the vehicle speed. Now we will fetch one PS product block. We'll search for it, PS product block. So here, once we get this, we are doing the squaring of this velocity. We are giving input and we are squaring V into V. We are getting the product V square, right? Now we will use one gain block, or we will use one PS gain block basically, as it's a physical signal or Simscape model. We are going to use this PS gain block where we will write half into rho value or the air density value we are considering as 1.225 kg per meter cube. Then A, or the frontal area of the vehicle, we are considering as 1.4 meter square. Then CD, or drag coefficient, we will consider as 0.3. So we have written this. We will click enter to save. Once it is saved, we will close it. Now, so this has been calculated. Now we will use one output port or out one port to connect this. Okay. So let me search for, okay. What we can do, we can search for output or connection port as well. We can search for it. Or we can simply leave it. It will be by default created. So let me just create one subsystem. So you can see one connection port has been created for it. Let me just name it as it is aerodynamic drag force. So let me write it as FAD. And this is nothing but the velocity. So we will write it as velocity so that we can identify later. This is nothing but our aerodynamic drag force subsystem. So let me write aerodynamic drag. Now we will calculate another road load, that is rolling resistance force. So the formula for rolling resistance force is Fr equals to mu Rr into M into G, where, let me just maximize the size. Here, mu R is defining the rolling resistance coefficient, M is the vehicle mass, and G is the gravitational constant. So let me fetch the blocks. So first we will use one connection block, connection port. So here you can see there is no input where we want to give, because we will set all the constant and gain value. So we don't require this connection port. So first we will take one constant block, PS constant block basically. So let me just search for PS constant. So this block, here we will set the value for the mass of the vehicle. We are considering here 1200 kgs. So we'll just give it as 1200. Now we will use a PS gain block. So let me connect this. Here inside the PS gain block, we will set the rolling resistance force into the gravitation constant. Rolling resistance force we are considering as 0.01. So based on the tire, it varies, and based on the road surface, it varies. So we are considering rolling resistance coefficient as 0.01, and gravitational constant we will consider as 9.81 meter per second square. Excuse me. Okay. So now once this has been created, we will create a subsystem for it. I have created one subsystem. Now let me just change the name, as it is rolling resistance force. Let me write it as rolling resistance force. This connection port is nothing but the rolling resistance force, right? Output of the rolling resistance calculation. I will name it as FR. Going back. Now we need to calculate another road load, that is nothing but the gradient force, or we can call it as hill climbing force. So to calculate that, the formula is FH equals to M into G into sine alpha, sine of alpha, where alpha is in the unit of radian. So let me just maximize the size a bit. So once I maximize the size, now I will start fetching the blocks to calculate this. Here we need one input, that is our alpha, as we want to vary the alpha value. So we will take one connection port to give input from outside. So let me just name it as angle. Now we will take one gain block. This gain block, okay, let me take PS gain block because it's a physical signal or Simscape block. So I will take a PS gain block. So PS gain, as the alpha is in radian, so whatever input in term of degree I am giving, I need to convert it into radian. So I will give the gain to convert it. So that is pi divided by 180. So pi is by default defined in MATLAB. So we can simply call the pi to get the value of 3.14, the pi value. So I will save it. Now I need another gain block. Sorry, I need one function block to convert it into sine function. So I will search for PH function, PS math function. And here I will set this to sine. Okay, by default it has been selected. You can see there are so many functions are available. So I need sine. So I will select it. I will connect it so that it can convert in term of sine. Then I need another gain block, PS gain block basically, to give the value for M and G. So M, or the mass of the vehicle, we have considered as 1200 kg, and gravitational constant we know it is 9.81 meter per second square. So we'll give it, and we'll put it inside a subsystem, and subsystem name will give as it is uh, hill climbing force or gradient force. So let me write as gradient force. And this connection port is defining the hill climbing output. I'll name it as FH or gradient force, whatever we want to call it. Let me just put it here. Okay, just a minute. Let me just drag this a bit up. This one also, let me drag it a bit up. Okay, let me just increase the size. Okay, fine. Now, uh, once this has been created, now we need to sum up the values to give input to as a force. Okay, we need to sum up the value. So we will search for a PS add block. In the PS add block, we will add this rolling resistance force and this gradient force. This one we have to add. We will, so sometimes many error comes like vector error. So to avoid that error, we are using here normal add block. And here, as it's a Simscape block and it is producing physical signal, so we need to convert it to physical signal to Simulink, as we want to use a Simulink add block. So let me just copy this. Let me just copy this PS Simulink converter. I'm just adding here and I'm giving the input here. And this thing, as this is also a physical signal, I need to convert it. I will give input to it, this add block. And now, as the calculation is going to create a force, so I need a ideal force source to give input. So ideal force source, I will search. So you can see this is the ideal force source. I will take this. Let me just rotate it. Okay. So, okay, fine. So as this has been converted to Simulink signal, so I again need to, once I need to give it input to this ideal force source, I need to convert it into physical signal. So I would need this Simulink to PS converter. I will copy this. I'll add it here. I'll give input to it. You can see. So to give the input these as velocity, we need one motion sensor. So I will search for ideal rotational motion sensor. So the, okay, not this one. Let me search for motion sensor. Let me search for motion sensor. Okay, this one. Okay, translational motion sensor. We'll search translational. Okay, let me search for motion sensor. Let me search for motion sensor. This thing will take, yeah, this one, ideal translational motion sensor. We need one input port to give the input for R, as R is nothing but the force. So you can read the description, whatever these ports are defining. So R is nothing but the input of force. C is the reference port where we can connect reference or the mechanical ground. V is the uh, velocity of these that will be calculated or that will be sensed, and P is the nothing but the positional displacement actually. Okay, fine. So we need one connection port to give the force as input. I'll just connect it here and I will name it as R. So we can recognize this thing. This V I need to give here. So I will just delete this connection, this port, connection port. I'll connect it here. So I have connected this. I need to connect one mechanical reference with this C. So I will search for mechanical reference. You can see this mechanical translation reference. We'll use this. Click Control R to rotate this, and I will connect it here. Now, we need to observe the behaviors, right? So, what we will do, let me just delete. Okay. So, what we will do, we'll just copy this here, one and here. Okay. So, this will sense the, okay. So, this one, this bottom one will sense the positional or displacement, and this one will sense the velocity, right? Okay. Now we need to, in this C port, we need to connect one ideal translation reference. So I will copy this. I'll click Control R to rotate this, and I will connect it here. So once connected, now, okay, let me just move these things a bit right. Okay. Now there's this one also right. Wait. Okay. Now what we will do, so this is the force which we want to give here as an input. So we need to consider one mass. So I will search for a mass that is nothing but the mass of the vehicle, and I will connect the mass with this R port. Okay, and I will give here this. The mass value, as you know, the vehicle weight we are considering as 1200. So I will consider this. So once this is connected, now this has been connected. Okay, so we need to connect one solver configuration as all the physical signal need to be connected with one solver. So I will take the solver and I will connect with this velocity. This here I will connect it here. So this has been connected. Now need to put it inside a subsystem. So I will search for create subsystem. Okay. Now let me just sort the size of these ports. Okay. So this output is defining nothing. So let me just name this thing so I can identify. This is the velocity, right? Velocity, or we can call it as speed. Let me write speed. This is the speed. Okay. This is the speed. And this is the displacement. So speed unit, let me also specify the unit. It is in meter per second. And this one is the displacement. So let me write the displacement. So this, its unit is in meter. Let me write it as well. Okay. So I've written this. Now let me go back. Now we will connect other ports by which we will run this block in a closed loop system. So our desired output we can get. Okay. Let me just maximize this subsystem block. Okay. So this one is nothing but our vehicle body subsystem. So let me just write it as vehicle body. Now, to give the input as the desired speed of the vehicle, we would need one step input. So we'll search for step, you can see. And inside the step, we will set the final value as 30 meter per second. Okay. We will use one subtract block to compare with the feedback. So we'll take this, and this is the actual speed which we are getting. So let me take this scope block as well. Now I will just maximize the size of the scope block. Okay. Similarly, let me take a scope block for monitoring this displacement. Let me just write it as displacement. So when we ever will open the or turn on the legends, we can see this one. Okay, let me write the signal name. This is the actual speed which we are receiving from the vehicle, right? Actual speed. This is the desired speed, right? Which we want to follow the vehicle, the desired speed. And from the actual speed, it is trying to feedback. So I will connect the feedback signal here. It will compare this subtract block, will compare the desired speed and the actual speed, and based on that, it will give the error to our controller. So here for the controlling, we will use a PID controller. Basically, we will use one PI controller here. We'll search for the PID controller block, and here in this controller option, we will set it to PI controller. So we have tested and we have find out that for this PI controller, this proportional gain value should be 4400 and this integral value should be 0.1 to control it effectively. So I will select it and I will click OK. So once this is done, we also need to observe the force. So I will name it as the force display. Display. This is the desired speed. Let me write speed, desired speed, right? Now we will search for one manual switch that will turn off if the manual switch and this desired speed value, this signal that we are sending and the desired speed value is not matching, then it will just stop. That's why we will use switch, but here we will name it as force. Okay. It will simply comparing this force value. If if it doesn't match, it will just stop this process, switch off the process, right? So we have connected it. Now we just remove the R block and here we'll use one ideal or the force source. So I will search for ideal force source. Same thing which we used inside this vehicle body. Okay, let me do one thing. Here we can see the subsystem inside it. Let me just turn off the content preview so that we can, yeah, fine. Now we are not able to see the subsystem, right? Let me just click controller to rotate this thing. Now this has been connected, this force. So as it's a simulink signal, we need to convert in term of physical signal. So we would need this physical to simulink converter. We'll connect it to source and we'll give the input to the source. Okay. And this thing will connect with a mechanical reference, mechanical translational reference. I'll search for it and I will connect this. You can see I have connected this thing. Now, what we will do, once this is connected, now we will simply add one solver configuration block with this. As previously I told that for each physical signal block, we need to connect one solver configuration block. Search for solver configuration block. So this block, I will connect it here, right? So almost our model is ready. Only thing is left, that is the angle which we want to give as input. I'll search for PS gain block. Oh, sorry, not PS gain. We will search for PS constant block. So let me connect the PS constant block here. Yeah, it's connected. For first simulation, we will set the gradient angle to 0 degree, right? So we are giving us 0. Let me just delete this thing as we don't require. Vehicle speed we can see the, okay, let me just change the name for our reference. Speed, this is the displacement, and displacement, this is the actual speed, and this one is the desired speed, right? Desired speed. Okay, we have connected all the required blocks. Now let's simulate the model for 10 seconds. So we have set it the time to 10 seconds, and let me just click the run button. Okay. Okay. So what we have done here, let me just delete this. Let me just connect this here with this angle. Okay, first let me save this block. Clicking save option, save as, let me save it in term of vehicle. Okay, let me just rename it as vehicle 1. Let me save it. So it got saved. What we will do, we will simply connect this uh, solver configuration with this angle, right? So as you can see, we are getting some error here. So let me just connect this here. Just connect this here. Okay, we have connected this. Let me run it. Okay, once I run it, you will be able to see the speed. Okay, fine. So you can see. Okay, fine. Let me turn on the legend so that we can identify the blue line and the yellow line. Right. So as you can see, this yellow line is defining the desired speed that we are giving as input with a step signal block. This is the desired speed which we want to get, and this is the PI. This is the actual speed which we are controlling using that PI controller. So we are getting like this, and the final value or the final speed which we have set it to 30 meter per second. So it's almost following the desired speed, right? If we see the displacement, we can see till 1 second the displacement is 0, and after 1 second it started moving, and its final value reaches almost to 60 or 270 something, 260 meter. Okay, you can see. Similarly, this is the force. You can see the force are starting from till 1 second it was 0, and when once the speed speed increasing start increasing, and at final point at 30 meter per second point, the force is the maximum. It's like 14, almost 13 into 10 to the power 4 Newton. So you can see, and again it got decreasing and it saturated in 0, right? So this is the process how we can model vehicle load with closed loop control using PI controller. So we can change the gradient angle. So now we have set it to 0. Let me change it to 5 degree. Let me see what difference we are getting now. So let me just run it. Let me save and run it. Okay, it is compiling. Okay, it's run. Now if I just open this, you can see the speed will be same, right? But it a little bit it increases beyond 30 as the gradient angle is increasing, and to cover that gradient angle, or to cover that hill angle, this vehicle needs to put more force, and so this top speed got little increased. So we can set the, okay, it's also some points here. You can see some distortion here. So we can change these KPKI value or the controller gain values, and we can optimize our vehicle performance. So thank you for watching this video. If you have came across with any doubts, please feel free to ask me. Thank you.